Yeah, I have started the simulation program, and I type now the system. This is my P controller. Note that we have designed it with gain 2. And now I have to add the PT1s. Block gain 1. The first one has 10 milliseconds. Okay. Second one have gain 1 and I think 1 second. Second one. Let's look into the workbook. This plan we want to realize 10 millisecond, 1 second, gain 2, 50 millisecond, gain 1, 330 millisecond, 3 PT1s. So we need a second one, gain 2 and 50 millisecond, and a fourth PT1 with gain 1 and 330 millisecond. Summing point in front, branches. We want to have a closed loop system. Block 5 is then the output of my controller, the process output. I think that this sensor is just skipped. I don't need the sensor. And I need a minus sign for this line. And this is now the system which we can now really investigate with a numerical closed loop calculation of the reference step response. Check what happens with my my predictions, and that goes with this button. I adapt the size of my window to my recording window. I want to have output block number 5. I want to have an input step of 1, just unit step function at the input. Time range should be 10 seconds. I have calculated the first maximum at 1.5 seconds, so I need 10 seconds to see what happens. And I click on calculation, and here you see the P controller reference step response. Overshoot is 20%, rather large for 60-degree phase margin, but I think we just look for this situation. The final value is 0.8, that means the desired value is 1, and this is the 20% error. We are 20% less than desired and ends up in the value 0.8. Of course, I can correct it if I just know this, that I'm 20% less than my desired value. I increase just my input step amplitude to 1.25. And if I recalculate this, then you see I get the same curve, but no, I'm ending up at 1. So this is a systematic error. The desired value and the control value differs in the P controller case with a gain 2 of 20%. Then I compensate this with a larger desired value. This comes from a potentiometer or from any other value, so I can adapt the scaling in a right way that the user has no idea that he sees a corrected control error. Yeah, but of course I want to go back to unit step function. The maximum here is at 1 second. I have predicted 1.5 seconds. You see, this prediction is rather very approximated, 50%. I have measured a 50% larger value, or compared with my predicted value at 1.5, this is 30% less. But it is an indication, an indicator. The indicator is helpful. It's not an exact predictor. Okay, I store this curve and we wait for the next step I want to do. Yeah, this is the simulation of the P controller. Let's do one step more. Yeah, what I want to do in the next step, 5 to 2, I want to change the phase margin. P-controller now with, to show you what influence has a change of the phase margin. Now I go to a smaller value. Why? We will see, just to check the influence of phase margin. Yeah, and if I go through the previous steps, then I know that the process, the open loop phase at omega d now is minus 180 plus 40 plus phase margin, and we see this is minus 140. I know this is identical to the process actuator sensor phase at omega d. So I have to find now the cross point of the new value of omega d, the cross point at minus 140. So I have to go into my curve in my paper, and we have to check where the minus 140 point is. You see, this is the next thick line here, and you see the cross point is not indicated now in this diagram. The cross point is now at 3, we can estimate 3.8. Yeah, omega d is 3.8. New omega d is 3.8 per second, and we can say at once, omega d is the speed indicator, we will be faster. You will see the signal goes faster up to my desired value. The not the settling time, but the rise time. Rise time is smaller. Furthermore, we go into the diagram, and now we have to find the value for the magnitude at 3.8. So this is, now I have not really a good, no, maybe you can see now this mark, this is 3.8, this is this line, and this line is at, I think, minus 10 dB. Now 3.8, 2338 is this line, hopefully you see this cross, and this is exactly minus 10 dB. In my note, we can say new f process magnitude at omega d is minus 10 dB. So we can say the controller magnitude at omega d now is, the sum must be 0 dB. Now I make the calculation, this is done here with factors. I can do this, of course, with dB values. The dB values are added, the controller dB value and the process dB value. The sum of both must be 0 dB. So we can say this must be plus 10 dB. And this is equivalent to a factor of 3.16. Just check. With 3.16. So our accuracy indicator, you see our XD with large times, then is 1 divided by 1 plus 2 times 3.16. Note here, this value is larger, so my error is smaller, and the final value is 0.137. So this is equivalent to a control error of 13.7%. I'm a little bit more accurate. You see, the gain is increasing. That means that our 20% error is decreased to 13.7%. We can very quickly check in our simulation. Simulation. I go to my diagram. I close my step response window and now change the gain of my P block from 2 to 3.16 and redo my calculation, and this happens. You see what happens? Phase margin goes down, means the damping of this curve is smaller. We have more oscillations. Yeah, we are faster. The rise time is smaller. We are faster in my direction to the desired value. More oscillations. Damping is bad. It's worse. And finally, we have here a final value which is nearer to 1. The error is now 13% instead of 20%. Okay, you see, yeah, if oscillations doesn't matter and we have a large tolerance range, maybe this 40-degree phase margin value could be better. That is a decision of specifications, discussion with the user. You can imagine what we can do now more. We can check how large could a gain be to reach instability. Yeah? If I make the gain larger and larger, you see, then the oscillations will be more undamped, and until there is a point where we have constant oscillations. Maybe we can find out this point in the next step. Yeah, in my next case, I want to check P controller with stability border, or at stability border. The border case, coming from Nyquist frequency, the border case is phase margin is 0. Negative phase margin means instability, positive stability, so the border is exactly the 0 value. That is the case where the open loop frequency at omega d, open loop phase, not frequency, open loop phase at omega d is minus 180. And the open loop gain, note that is the definition for my Nyquist border, is 1. Here we have exactly the sinusoidal oscillator condition. If we have this and a negative feedback, we get with this phase shift a positive feedback with a gain 1, and then you have a sinusoidal generator with constant amplitude. So look, what this is a result. The open loop phase is again the point of my process actuator sensor value at omega d is a minus 180. In our case, in the P controller, we have no controller phase, and you see the omega d value out of my curve is now that point where we crosses the minus 180 line. It is here in our case the second last horizontal line. This is my minus 180. Here you can see the cross point at this is 9, this is 8. This is a cross point, and we can find out that this is nearly 8.2. 8.2. So omega d is calculated to 8.2 per second, and f process actuator sensor magnitude at this value is then, back to my curve with scaling, this point here 8.2 is I think this cross point. I'm not sure if you can see this, and I can reach negative 24 dB. Negative 24 dB. So this is the case if the controller KC is positive 24 dB, and the value we can calculate with our calculator is 15.8. So if the gain Kc increases to 15.8, then we assume a phase margin of 0 and a process phase of minus 180, a gain 1, and then we have a sinusoidal generator. Let's check if this can be checked with the simulator. Note that the Bode plot, of course, is, was war das, 15.8, has of course some inaccuracy in the reading. 1 dB is 12%, and 1 dB in our case is the distance, the half of the distance of two small lines. So I think we cannot exactly reach this point, but it doesn't matter. If I calculate this, you see I'm over the point. Now this is instability. Maybe the number of calculations could be increased. And yeah, if I do this up to 200, you see no change here. 500, that means 15.8 is too large. But you should be clear that the accuracy of the reading of magnitude values with the Bode plot is less than 10%. Cannot be better than 10%, because 10% is less than 1 millimeter. So the border is a little bit smaller. So if I go to this point and say try it with 15, say okay, calculation. Only not better, but the amplitude goes down. Yeah, with some experiment, of course, I can find out. Testing other values, say 14. Okay, click. Now as you see, I'm reaching my border value, maybe 13 or so. Doesn't matter. You see, this is a good method also to find out instability points, and we should be far away from this gain K, otherwise we get a small bad damping. Okay, so far we go back to P controller with 60-degree phase margin, and we can just look into our table what we can fill in. In the student paper on page 85, you can see these three cases. Omega D is increasing, KR or KC, here the name is KR, that's my controller gain. KC is also increasing up to 12.6. You see, in that calculation I have got 12.6. Okay. And phase of the controller is 0. This is a control error. This had no sense to define the control error. I think this is just a good check what happens if you change your phase margin value of the P controller. In the next rows of the table, I want to stay with 60-degree phase margin. Yeah, the damping should now be constant for all other types of controllers at 60 degree, because the damping here is too poor. After a view into my student paper, I've seen that in the past I have calculated in here this value to negative 22 dB. I just go back to the Bode plot, and that's really true. Not 24 is wrong. If I go up at 8.2, I see this point, and this point is negative 22. Yeah, if you check very accurately the cross point with this system, then you are at negative 22. So I have to correct this value with red. Yeah, better reading, negative 22 dB, and then this ends up in a KC. This is plus 22 dB, and then this value ends up in the value 12.6. 12.6. And if I go to my simulator and I change to 12.6, maybe then this fits better. Yeah, 12.6. You see, now I on the other side of the border, now in the stability region, so I think the exact value maybe is 13. So you see, this is a P controller. We cannot reach the exact final value 1, because if we make k larger and larger, we reach this instability point, and there is a natural limitation of the size of kc. We have to find another way if we want to have a control error 0. This comes then with the next video. This is ends up in video number 51. Yeah, video 51.